We're gonna start radicals today. Let me go back up to the notes. Might be in a different. It's in here. Yeah, I think it's in here. Let me find these notes. Yeah, here we go. So we kind of talked about this before a little bit. So I'm gonna review it, and then we're gonna jump in and do some examples. All right. So we talked about the radical mechanism being different from a polar mechanism. And let me make another page so I can put some information on here. All right. So we talked about the before polar mechanisms. And we talked about with a polar mechanism, the fact that you have different types of bond making and bond making processes. We talked about homo and hetero, either lytic or genic, right? Bond forming, a bond breaking, a bond forming. And we talked about the fact that when you do a polar mechanism, you moving 2 electrons at a time, right? It's always one atom giving 2 electrons, or one atom accepting 2 electrons. All right. So I don't know why that other information is showing up. Let's see. All right. So also with the polar mechanisms, we talked about the fact that you have a nucleophile and an electrophile, right? And the nucleophile is a sink, and the nucleophile is a source, electrophile is a sink. So with the radical mechanisms, it's kind of different. First of all, you don't have a nucleophile or electrophile, right? So with a radical mechanism, and I'm just giving you an overview. I'm gonna go back and look at what we already talked about, and then we're gonna jump into an example to apply it. So for a radical mechanism, everything is 1 electron. We talked about that already. So your arrow is actually going to be instead of a double-headed arrow, it's going to be a fissure, right? All your curved arrows and radical mechanisms are single-headed arrows, right? And we said that all of your bond making and breaking is homo, either lytic or genic, right? Homolytic is bond breaking, homogenic is bond making, but all of your bond making and bond breaking is either homolytic or homogenic. All right, so it's 1 electron, everything is homolytic, everything is homogenic. And then for the reactions that happen through this pathway, we're going to talk about today about radical substitution. Right, so radical substitution. So let me give you an example of that. Actually, let's go to the notes on that. So where is it? Come on. Let me find it. Here we go. All right. So we've already talked about substitution, elimination, addition, rearrangement being the reaction types. So with radical substitution, which is what we have shown here, it is a substitution. In this case, you're substituting a hydrogen that's shown here with bromine, but it's just not a direct substitution, right? It's an example of a substitution. And one of the things that has to happen for radical substitution is you have to remove this not a proton, remove this hydrogen and replace it with a bromine. But since it's radical, it's not a direct replacement. So we talked about there being 3 steps, right? Initiation, where you break apart the bromine into 2 bromine radicals. And then those radicals go now and start walking the chain, pulling off hydrogens, right? It's called, that process we said was called abstraction, or the removal of H dot. And then every time that happens, it happens the exact same way, where you have the bromine giving up 1 electron, homogenically making a bond with hydrogen, and at the same time facilitating homogenic bond breaking between carbon and hydrogen that's shown here. Right, so that's carbon, that's hydrogen, and you're breaking the bond between them homolytically, right? And this is always a 1 electron process. So once you do that propagation step, right, you have your hydrogen that's over here. Your radical, your new radical that's over here. And then with that new radical, now you're going to terminate that and get to the substitution product, right? So now you're going to take that new radical and react it with a bromine. And then when you do that, right, you make a new bond between carbon and bromine, and you get to the substitution product. All right. So now let's talk about that in more detail, because obviously there are other hydrogens on that chain that can be removed. And so we're going to talk about that now on the other part of this handout. So let me get to that part of the notes. It's actually the back page of that handout. But before we do that, let's go ahead and let me erase all this stuff. Let's go ahead and do a little bit of arrow pushing warm-ups, and then we're going to actually take this and apply it to an example. All right. So in the first reaction, you can see here I started out with a bromine, and then on this side I have 2 bromine radicals, right? And each bromine has 1 electron. So what that means is that I broke the bond between them, and I broke it homolytically, right? So I'm taking this pair of not the pair, but I'm taking this bond, and I'm going to take an electron and do this, and then I'm going to give 1 electron to the other side, right? And what that means now is that I'm going to lyse that bond or break that bond, and each one of those bromines, right, is going to take 1 electron with it. And that's how I end up here. Right, where I have 2 bromine radicals. And again, a radical is an atom with a single unpaired electron. Right, I should make a note that when we're talking about radicals, normally this is reserved for nonmetals. Right, because you have metals like sodium that are 1 electron donors, lithium 1 electron donors. So when you're talking about something that's a radical, that terminology is normally used for nonmetals, not metals. All right. Okay, so now let's look at the second example, right? You got 2 bromines, the 2 bromine radicals coming together, right? To give you a new sigma bond between bromine, the 2 bromines, right? So the way you show that is instead of one atom giving both electrons, right? Now each atom is bringing one electron, right? So I'm going to show that like so. I'm going to show an electron coming here, and I'm going to meet that arrow with another arrow coming from my bromine. When I show those two arrows coming together like that, that means that I'm making a bond between bromine, well, one bromine and the other bromine, right? So that is homolytic or homogenic.
Homogenic.
Homogenic, right? All of your radical processes are going to be either homolytic or homogenic, right? So this is homogenic bond formation. All right. And then if we go down here, we can see an example of a radical addition. How do I know it's an addition? Which one of those star materials tells me that this is going to be an addition reaction?
What did you say?
Which one of the two starting materials over here is letting me know that this is going to be an addition reaction?
The bro.
How do we normally classify addition? What do we say we always look for when we're doing addition?
Is it a double bond?
Pi bond, right? So the pi bond right here is telling me that this is going to be an addition. Pi bonds cannot do substitution, right? They can do addition, and then the reverse of addition is elimination. All right. So now let's look at how this happens. I'm going to erase that. All right. I'm going to actually take one electron from the, actually, let me do this to make it make sense. I'm going to give an electron to the double bond on this side. I'll take one from here and take one and put that arrow onto carbon. Right? It's very important that I show that arrow stopping on carbon, because that's what my electron is over here on carbon. Yes or no?
Yes.
Right. That in any pi bond, if I do it, you know, if I'm reacting it under radical conditions, any pi bond can be broken up into, and I'll show you an example right here. Right, I can take any pi bond and break it up. Right, into two electrons like that. Because every bond is made up of two electrons. So anytime I break a bond, it's either going to be in a radical fashion where everything gets one electron, or a polar fashion where I'm bringing two electrons and making a new bond, or if I break a bond in a polar fashion, one of the atoms is leaving with both electrons. All right, we okay so far?
Yes, sir.
All right.
Yeah.
What about this example right here? What would you do? What happened in this example?
A bond formed between the two.
So the two rings, you made a bond between them. Exactly. Right? So I'm going to take that. And how would I show that since I'm working with two radicals?
You bring the electrons together.
Yeah, so I would just show the electrons here, right? And I kind of show them meeting up together, meaning that they are going to be, sorry about that, they're going to be shared between those two atoms. All right. What about the example below? Right? Because I think that the ring is pretty straightforward. What did I do on this example right here? Look at the star materials, look at the product, tell me what I did.
So you formed a bond between the bromine and the hydrogen.
Good.
And then broke the bond in the hydrogen
and carbon.
Cool.
Good. That's exactly what happened. And so the way I would show that, anytime you want to show, this is an example of abstraction. Anytime you want to show that abstraction, it's the same, and I'm doing this on purpose. It's the same exact mechanism for abstraction every single time. Anytime you're pulling off a hydrogen, you're going to break the CH bond homolytically. Can y'all see that? So you're giving each one of those atoms in that were involved in that bond 1 electron. And then you're going to show a bond forming between bromine and hydrogen. Again, all of my arrows are fish hooks. Right? And so that is the mechanism for abstraction. I'm saying that because every time we do a radical substitution mechanism where we got to go down the chain and pull off hydrogens on each carbon, that's what we're going to be doing. That's abstraction is central to every propagation step. Right, so every propagation step is going to have, that's what's happening, abstraction. You do abstraction multiple times down a chain, right? And you see over here, the result of abstraction is always a radical left over, right? Some new radical that you made. All right, what about the bottom reaction? Let's look at that real quick. And I think there's a couple of examples we're gonna work on up top, and then we're gonna hit this last worksheet that's in this handout, dealing with radicals and then determining the percentages of how much of each radical we'll get and all that. It looks like a lot, but it's actually not that bad. And don't let that, when we get to that equation, don't let that intimidate you, right? It's just a fancy way of taking an average. All right, what do we have here in the bottom example? What would you do?
Bromine bond.
You made a carbon bromine bond. How would you show it in a radical fashion?
The atoms meeting up in the middle.
Meeting up in the middle, right? You like me, I like you. Boom. Let's meet up and let's make a bond right here. Right? That's it. This is an example of a termination step. That's an example of termination. So termination is always going to involve bond formation, right? Right, so anytime you're doing a radical substitution, the termination step is the final step in that substitution. All right. Any questions so far? Let me go up here to this other part of this handout. I think there's some radical examples in there that we can mess with before we jump to this big example. And the same, let me say this too, the same rules apply as it relates to finding delta H, finding KEQ, all the same rules apply. I can still go in and figure out what the bond strength is of each one based on the chart. I can still figure out what bonds broken, the delta H is using bonds broken minus bonds formed. It doesn't matter if the bond is broken homolytically or heterolytically or is formed homogenically or heterogenically. It doesn't matter. The same process applies if I wanted to calculate delta H for a reaction, even if it's radical. Let me see here. There's a couple of radical. Yeah, let's do D right quick. And then we're going to jump down and let's do D. And I think that's all the radicals that's up there. But we got a whole example to work through. So don't sweat that. All right. What is D? What is it showing? What type of process is D showing? If you can't see the arrows, this arrow right here, I'm gonna make it black so I can trace over. So this arrow right here is going back to carbon. It's a fish hook, right? This arrow is coming from here. That's a fish hook. And then this is a chlorine radical where this arrow is coming from, sorry about that, coming from chlorine, like that. What's the name of that process and what will we get from it? Don't let the birds out talk you now.
Is it abstraction?
Abstraction. It's abstraction. You're pulling off or removing H dot. Am I right? Right. H dot is a colloquial term now. Sometimes when you say that around certain people, they get mad because they think you don't know what you're talking about. But you're removing a hydrogen radical, right? I had a professor who used to get mad when we said H dot in grad school, but it's all right. If you say H dot, I won't be offended. All right, but it's an abstraction. Right, and the fact that it's an abstraction that's facilitated by a chlorine radical, right? What do we get on the other side? We're gonna get what? HCl, is that right?
Yes.
Plus what? What's the radical gonna look like?
It's just gonna have one electron on the right side of carbon, that carbon.
Is that right?
Yes.
Yeah. Anytime you do abstraction, you're gonna be left with an atom somewhere that has a single unpaired electron. So abstraction is the way you make new radicals. It's a process for making new radicals, right? So, and it happens in which step in the mechanism? Because the radical mechanism is always going to have these same 3 steps. It's going to be initiation, followed by propagation, followed by termination. So which one of the steps does abstraction happen in?
2.
Huh?
The propagation.
Propagation. Good. Good. Don't be scared. Just say it. All right. Let me see if there's any more radicals up here. I don't think so. I think we did the other one already. We did D and discussed that. So now let's go down to this page because we're gonna work through a radical substitution. And it may take us this class and the next class, but we're gonna get it done. Man, that's a lot of notes. Okay, so now on this example right here, it says calculate the product distribution. I'm gonna read this and then we're gonna decipher it because it sounds like a lot when you read it. Calculate the product distribution for monochlorinated products for the reaction of pentane with chlorine on the radical chain reaction conditions. Oh my gosh, Dr. Russell, I can't do that. All it's asking you to do is give the products, right? And then determine how much of each product you're gonna get. But if you see it in the book, it's not gonna say it like that. It's gonna say it like this, right? So let's talk about what product distribution is. That's a term that we need to know. So product distribution, that simply refers to the ratios of products, right? So the ratio of products when competition is involved, right? So you have a reaction that has competitive processes happening. You always get a ratio, a certain ratio or distribution of different products. All right, so the product distribution is the ratio of products when you have competitive processes occurring. All right, it's a word that you're gonna hear a lot. You're gonna hear it again in part 2. You're gonna hear it all the time. You're gonna hear it even more here. So It's best to know what the definition is. So it's the ratio of products when competitive processes occur. All right. What does mono mean? Anybody? Not the sickness, no.
One.
One. So a monochlorinated product is a product with a single chlorine in it, right? That's what monochlorinated means. I'm gonna put singly chlorinated. So a monochlorinated or singly chlorinated product. So pentane is my starting material, and I'm redoing it with chlorine. And then it says under radical chain reaction conditions. So this is an example of what we call a radical substitution. And the reason it's called a radical chain reaction is because once you start that propagation part, it's hard to stop it, right? Radical reactions are not the preferred method for substitution because they're very difficult to control and you get a lot of different products. Because sometimes you can have two radicals combining in termination that you didn't intend to combine, you didn't want. I'll show you that when we get to the termination step. It's a process. Dang, I just had the name on the tip. It'll come back to me. It'll come back to me. Disproportionation. That's the word I'm looking for. But we'll talk about that in a minute. So you have pentane. Let's do this. Let's draw out all the hydrogens on pentane because it's important when you're doing a radical mechanism. It's very important to understand where your hydrogens are because you need to know that to know what you're going to abstract. But it's also important to know what's the same and what's different. All right. And then here, you got hydrogens here, and you got hydrogens here. Anybody disagree with that? This goes all the way back to week 1, when we talked about skeletal forms and how every vertex is a CH2 and the end of every line is a CH3. Is everybody okay with that part?
Yes.
All right. Heard one person. Yeah, no problem. All right. So when we look at this molecule, we can see that it's kind of got some symmetry here. Right? So both the left and right side are identical. And so when you do your radical substitution, right, for the purpose of this problem, we're only going to focus on one side. So we're going to focus on these 3 carbons right here because the other 3 carbons are identical. But the other 2 carbons are identical. So you can see that this carbon and this carbon will be the same, right? And then these 2 carbons will be the same. Are y'all following that?
Yeah.
So we're only going to focus on let's say the left side. So we're going to do this side right here. I'm trying to pick a different color highlighter. So we're going to do this side. The carbon in the middle doesn't have anything to compare it to, so you're going to work with that too. So first, what I want to do is draw the products out. And then we're going to go back and do the mechanism and show how you got each one of them. So one of your products is going to look like this. You got a chlorine here on that terminal carbon. One of your products is going to look like this. Where you got a chlorine here on that secondary carbon. And then this is plus, obviously. And then plus. One of them is going to, the monochlorinated products. One of them is going to look like that, right? Anybody not see that? Go ahead, Amari.
Oh, how did we get the product? How did we get these 3 different?
Yeah, so we're gonna go through and look at each one of them. and
Okay.
how we made them, right? Because this is the whole purpose of doing going through the mechanism, the initiation, propagation, and the termination. So we're going to show that, right? But you do, for those of you who are engaged, you do see that if I put a chlorine on this end, it'll be the same as this product right here, right? The chlorine would just be on the other end. Are y'all following that?
Can you
Yeah.
say it one more time?
All right, this is what I'm gonna do. I'm gonna draw out the other products to prove that I'm gonna draw them in a different color to prove that we don't have to show that other side. So if I drew this as a product, and we're gonna name them, and that's gonna help us to understand.
Are you saying it's like the same thing but backwards?
Yeah, it is, exactly. That's exactly what I'm saying. Right, so if I took, if I react to this side or this side, I'm gonna get the same thing. That's the point I'm trying to make. So that looks like water, a wave. It's not good. So if we name these, we got 5 carbons, 1, 2, 3, 4, 5, and then a chlorine on the first carbon, because we always start counting from the end where the closest substituent is. So this is 1-chloropentane. All right, what do we have up top? Is it the same? Uh-oh. 1, 2, 3, 4, 5 carbons, is that right? Where's chlorine? It's on the end, isn't it?
Yes.
Yeah. So when we name that, we're going to start counting from the end where chlorine is. So this would also be what? 1-chloropentane. Yes or no?
Yes.
Yes.
All right. What about the other product, Maury? What do you think about that one? So we got 1, 2, 3, 4, 5 carbons. Is that right?
Wait, are you talking to me?
Yes.
Oh, okay. Yeah.
And then where's chlorine in this case? Is it on the first carbon or the second carbon?
The second.
Second, right? So this is 2-chloro. Be consistent with my colors. This is 2-chloropentane. Right? What about the one above it? Is that also going to have the same name, 2-chloropentane? Still 5 carbons, and the chlorine is on the, we start counting from the end closest to chlorine. So how would you name that one?
3-chloropentane.
Well, look where chlorine is though. It's on carbon number 2, right? 1, 2, 3, 4, 5. Is that right?
Oh, I'm sorry. I was looking at the one after that.
Yeah.
Okay.
Even on that one, we'll have to start counting from this end. You always start counting from the end closest to your first substituent. Right? So this was, let's see, 2-chloropentane, and up top, it's going to be the same thing. I'm just trying to make the point that if we show one side, right, because of the symmetry, we don't have to worry about the other, drawing out all the other products because they're going to be identical. Are we on the same page here? Now, what if, Amari, I think you're right about this product, right? That is.
Yeah, that was the one I was referring to.
Okay, yeah, you're right. That's 3-chloropentane. But since you don't have anything in that molecule to compare it to, then, we don't have to worry about a duplicate product, right?
Oh, okay.
All So that would be 3-chloropentane. So that allowed me to sneak you some nomenclature, because I hate teaching it because it takes an inordinate amount of time to teach it because there's so many rules. But I like to teach it in bits and pieces as we go. All right. So now let's go through this mechanism and let's see where these three products are going to come from. All right. So in the initiation step, are you serious? All right. Hold up. I got to reshare my screen. For some reason, it dropped.
Dr. Russell, if you're talking, we can't hear you.
What about now?
Yeah, we can hear you now.
Thank you, man. Appreciate that. All right, so in the initiation step, I'm going to take chlorine and I'm going to break it up homolytically. And I'm going to use UV light to do it. So that's why you see H nu, which is the energy of a photon, E equals H nu. So I'm shining light on this and I'm going to break this in half homolytically, like so. So I'm going to get a chlorine radical and another chlorine radical. All right. Keep in mind, I'm not going to write that out. I'll just write out the number. I have 6.02 times 10 to the 23rd molecules per mole of chlorine. So don't worry about running out of chlorine, right? When we have to do all these propagation steps and termination, you will not run out of chlorine. All right, so you have Avogadro's number of molecules per mole of chlorine. So don't worry about that. All right, we're okay with that? So now in the propagation step, what am I going to do in propagation?
I'm sorry, Dr. Russell, where did the two chlorines come from?
Right here. I took the chlorine that I had up here, the Cl2, and I
okay.
broke it in half.
Gotcha.
Yeah, that's what happens in every initiation step. Your initiator might change, but the initiation step is always going to be the same. You're always making some type of reactive radical. All right, so in this case, chlorine is my reactive radical. So then when I get to the propagation step, that's going to be where my abstraction occurs. So I'm going to draw out my chlorine radical, right, plus pentane. All right, I'm going to start here, since we started here up top. You okay with that? Anybody panicking, scared? Hopefully not.
Dr. Russell, I don't know if it's just me, but it's like you're breaking up.
Is my audio breaking up?
Yeah.
Yeah, I can hear it too.
Hold on, let me grab some headphones. I don't know what's going on with this stupid computer, but
I mean,
good
it's
now.
working right now.
Pretty clear. Yeah.
am I clear now?
Yeah.
All right. So now let's see what this looks like. So what, again, in abstraction, what's happening again?
You're removing an H dot.
Removing H dot. Which one do you want to remove? The one on the bottom, the one on the top? It doesn't matter. The one on the other side?
Top.
The top? All right,
Yes.
you would pick that. So I got to erase this part. It's okay. You already got it though. and I'll write it back in before I post the notes. So again, I'm going to give an electron. I'm going to change the color for the arrows. I'm going to give an electron from chlorine. Boom, like that. Is that right? And then I'm going to homolytically break the CH bond, like so. Here, and then here. One electron back to carbon. Anybody not see that?
And where's that chlorine electron going to again?
It's going to pull off the H dot. Can you see that? These two are kind of meeting up.
Yeah, okay.
Yeah, so that means that the hydrogen is coming off, but it's being facilitated by chlorine. All right, so on the other side, now I have a new radical. That's what happens in propagation. I abstract the hydrogen, and in the process, I make a new radical. So on the other side, I have a radical that looks like this, where this is now plus HCl. Yes or no?
Yes.
All right. So now let's do the other one. Let's do,
I have a question.
go ahead.
If there's only 2 CLs, but there's 3 places with CL.
I just explained that up here. Let me show you. See right here where I put Avogadro's number?
Mm-hmm.
So you have that many molecules of chlorine per mole.
Okay.
You feel me?
Mm-hmm.
Or atoms per mole.
Okay.
So if I start with 1 mole of chlorine, then I got Avogadro's number of atoms per mole or Avogadro's number of molecules per mole.
Okay.
Make sense?
Sorry. Yes.
So you will not run out.
Okay.
Yeah. You got enough chlorine to choke a horse. You won't run out. All right. And then, so in the second propagation step, I'm going to show the step where I'm pulling off these hydrogens right here. Is that right? So it's that plus chlorine. And somebody tell me what's going to happen. Something's going to happen, right?
Right.
So does anything change? Anything different? I'm still going to have the same 3 arrows. This one's coming here. This is going with H. And then chlorine is coming to facilitate that. Nothing there, no different. The location is different, but the process stays the same. So in the product, I'm going to have this radical now that I made. Not the product, but yes or no? And that other hydrogen, don't forget that, that's still there. Let me show it, because somebody gonna ask about that. Where'd it go? It never left. It's still here. You got a radical right there. Are we okay so far?
Do you recommend writing out all the hydrogens
Yes.
until we get used
Yes.
to it? Okay.
Yes. Always write them out until you get to the point where you don't have to worry, you don't have to think about it. Is everybody cool for now? We good?
Yeah.
All right. Now, what about the third set of protons, third set of hydrogens? That's going to happen here, right? And it's going to be the exact same thing. Another chlorine is going to come in. And boom, we're going to abstract here, right? Here, here, and then this is going back to carbon. So what I end up with is this new radical now in the propagation step. Let me put the hydrogen back first. I'm gonna break my own rule. Is that right? Anybody not seeing that? I put those boxes up there on purpose too, to kind of help you to think from left to right and think about what's happening each time. All right. Anybody have any questions about what just happened in propagation? All right. So now let's terminate this. And this, again, if you think about the termination part, one of the things that can happen in termination is your radicals that you made in propagation can also combine. So that's why this is a not necessarily the most desired process to use for substitution, because you can combine any radical. So you get a lot of side products from this. All right. So let's look at in termination. We're going to take every radical we made in propagation. So this one, oh, no, the radical was up top. And then the other radical that we made, which is here. And the other radical we made, which is here. All right. Yes, no?
Yes.
And then we're going to combine each one of these with a chlorine. Right? Each one of those is going to be combined with a chlorine radical. And again, why am I not running out of chlorines?
Because you got a whole bunch of them.
I got a gang of them, and I won't run out, right? You're going to have enough chlorines, and then anything that doesn't combine with a radical in propagation can recombine with itself. So you never run out. All right? So now in the termination step, this is where my products are formed. I don't want to say substitution, because so that's the product formation step, and everything here is homo what?
Jenny.
Genic. Good. Because I'm making carbon chlorine bonds in this case. So everything is homogenic. All right. So how would you show that first step? How would you show the chlorine combining with that radical?
You'd have an arrow from the electron on carbon to the
Like this?
But they need to meet up.
Yeah.
Yeah.
So like that?
Yes.
That would work, right? And so that's going to give me this product right here. So boom, like that. Sorry about that. With a chlorine on this carbon down here. Let me write out the CH2 so you don't lose it. So the chlorine is going to be here. But I could also write it like this and keep it in skeletal form. Right? Either way is fine. All right. What about for the second product? What are you going to do there? Anything different?
No.
Please don't say yes. Same thing, same process. One electron from each atom. It's all homogenic. So the product looks like this. Is that right? You can show the hydrogen or not show it. It doesn't matter. And then on the final product, it's here, right?
Yeah.
Here and then here. Those two coming together. All right. So when you look at that process, it looks like a lot, but at the same time, it's really just if you understand what happens in propagation and you understand which hydrogens are different, right? That's where your abstraction is going to happen. So once you do the abstraction part, it's just a matter of keeping track of which radicals you made, right? So the way, and we got to stop here, but the way that you get the percentages or the product distribution is going to be based on the types of carbons you're working with, right? So I'm abbreviating product as PDT, product distribution in a radical substitution is based on the primary, secondary, or tertiary carbons. That are present, right? Primary, secondary, tertiary carbons that are present. That's how you determine the product distribution. That's how you determine what percentage of what products you're gonna make. And just for the record, the more substituted carbons usually predominate as far as like the percentages are concerned because they make more stable radicals. But we're gonna talk about that Wednesday. All right, any questions about anything? All right, no questions. All right, so if that's the case, then I'm gonna stop the recording. I'll post these notes to Blackboard, and I'll post the video to YouTube. So have a good afternoon, and I'll see you back on Wednesday.
You breaking up again.
I was just saying bye.
Oh.
Bye.
Bye.
Bye. Have a good one.
All right, y'all take care. Have a good afternoon.